Hello everyone, thanks for coming. I would like to present my quick vector autoregression models with skewness and heavy tails. This is a joint work with Sun Kasan and Stepan Mazou from Örebro University. So the motivation of research is that the Gaussian vector autoregression models have become one of the key macroeconomics models for policymaking and forecaster based on the survey of Kasan in 2013. However, one of the problems of the Gaussian VR models is that macroeconomic downturn during recession and crisis can hardly be explained by a Gaussian structural shock. So people have tried to extend the Gaussian VR models for a more realistic assumption of the data. For example, VR models with stochastic volatility models, which help to improve point forecast and also density forecast. Then time-varying parameters can be added, but empirically the evidence is mixed. And recently there's a lot of efforts try to combine VR models with heavy tail distribution. And this seems to be a reasonable way to go because the non-normalities and fat tail characteristic of macroeconomic variables has been documented in many studies. For example, in the paper Fagiolio and Ascaris, they try to fit the marginal distribution of macroeconomic variables with a different distribution, and they find that the exponential power distribution is preferred, while in case of VR models, Ni and Sun, that is the first one that proposed a multivariate student T VR models, and follow them, Curie and Chip try to apply very similar ideas for DSV models. In the paper, Smith that first come up with an application of multivariate skew VR models for the spot price of electricity in Australia. However, these models only allow for one parameter to control for the degree of freedoms and then somehow restrictive. So still there's a gap in the literatures for a combination of heavy tails, skewness, and stochastic volatilities for VR models. And in this study, we want to fill in this gap by propose a general class of generalized hyperbolic skew student T distribution with stochastic volatilities. And in empirical illustration, we find that fat tails model really improve in-sample goodness of fit and also out-sample forecast in comparison to the Gaussian models. Even though we find a very slight evidence of skewness, but we send an important message that if the models have stochastic volatilities, then the problem of skewness will become more important. So for the rest of the talk, I will introduce the VR models, the Gaussian VR models, and then show how we extend the Gaussian VR models using two strategies. The first one called orthogonal skew VR models, and the second one called multi-skew VR models. I will briefly mention how we make inference on these models before empirical illustration. So the Gaussian VR models with stochastic volatility can be written in the first equation. Yt here is a k-dimensional vectors of the endogenous variables that is regressed on its p-legs and added with a Gaussian structural noise, where here C is a vector of constant, and B here is a regression coefficient matrix, and the matrix A is a lower triangular matrix that describes the contemporaneous interaction of endogenous variables, and HT can capture the heteroscedastic volatilities of the Gaussian structural shock epsilon. And then we assume that the process of HT is a random walk as standard assumption in the literatures. So in short, we can write Yt in terms of multiple linear regression with a Gaussian structural noise Ut. And the idea here is that we will extend the Ut for a heavy tail distribution and skewness. So if we write A times Ut left with a diagonal matrix times with vector of independence Gaussian, that makes a k-dimensional vector of orthogonal shock. So the first step is that we will write this orthogonal shock in terms of a mixture of mean and variance. Here gamma is the mean vectors controls for the skewness parameters, and WTs is the mixing variables. That is a diagonal matrix that contain the element psi follow inverse gamma distribution, with nu is the degree of freedoms. So equation 4 is just saying that the stochastic representation of the orthogonal shock is just a vector of independent univariate generalized hyperbolic skew student distribution, and it nests the orthogonal student and the Gaussian VR model as the special case. And if we think about UT, it's just nothing as a linear combination of the orthogonal shock in this case. So in orthogonal models can be written in terms of mixtures of mean and variance of the Gaussian shock. Instead of imposing in orthogonal shock, we can have another strategy by imposing the fat tail and skewness directly in HBAR equation by writing UTs as a mixtures of mean and variance in this case. So compared to the LSQT VR model, the MSQT model is just saying that in HBR equation we have innovation that is fat tails and it have fat tail and asymmetries, and it's correlate to each other's equation. And we also have the tail curve movement by restricting all the mixing variables equal to each other's, that make the marginal distribution of UTs is a multivariate generalized hyperbolic skew student T distribution as a special cases. And it also becomes a multivariate student T's when all the mixing variables equal to each other and the gamma parameters for the skewness equal to 0. So the Bayesian inference is extended to estimate these parameters. We will show more detail in the papers. But here we employ the Minnesota style priors for coefficient B, and we let the skewness parameters gamma to follow the normal distribution with mean 0 and variance 1. The degree of freedom follow a gamma distribution, so that the mean of degree of freedom go around 20s. And for other parameters, it's very standard, follow Gaussian VR models with stochastic volatilities. So for the empirical illustration, we will show an example of 4 variables VR models with industrial production, inflation rate, and unemployment rate with the VIX. The data is collected at monthly frequency from January 1970 to December 2019. And we have 14 VR models with and without stochastic volatility, and with different setup of distribution in this case. And then we calculate the recursive outsample forecast during the period of 2007 to 2019. And in order to compare among 14 models, we will calculate the marginal likelihood for the in-sample units of fit. And for our sample forecast, we will compare the point forecast using the mean square forecast errors, and the density forecast using the log predicted density and the continuous rank probability score, the CRPS. So in this table, I will show you the log marginal likelihood of the 14 models with and without stochastic volatility. And as you can see, if we have stochastic volatility models, it really improves the log marginal likelihood over the models without stochastic volatilities. And if we move from Gaussian to more complicated distribution, we will see that the marginal log likelihood improve over the Gaussian in this case. Interestingly, for the models with OSQT and MSQTs have the maximum log marginal likelihood, and then it is preferred over the Gaussian and the student case. So here is another plot for in-sample data. We show the posterior samples of fat tail or heavy tail parameters and skewness parameters gamma in case of MSQT models with and without stochastic volatilities. So as you can see that in case of industrial production, the models without stochastic volatility estimate the degree of freedom go around 5 and 6, something like that. But if we include stochastic volatilities, the fat tail parameters become less important and it's go around 20s. On the other side, we will see that the skewness parameters before go around 0 for the model without stochastic volatility. But if we have stochastic volatility in the models, the skewness parameters when goes up to 0.25. And we reach an important message that if we have stochastic volatilities, the fat tails become less important, but the skewness become more significant. And here we also see a very similar things for inflation. Here we'll see that before the skewness parameters go around 0, but now it fluctuates more and it becomes more significant in this case. So for our sample forecast, we will compare the probability integral transform, the PIT histogram, and here I illustrate for 4 models: the student, O student, and the multi-student with the O skew-T and M skew-T. We will see that for industrial production, inflation, and unemployment, they are more or less very similar to each other. But in the VIX case, where we have a clear distribution of skewness, then the O skew-T and M skew-T seem to be underestimate or overestimate in one tail, where the O skew-T and the M skew-T have more accurate prediction in the tail over the student distribution. And here is the last plot where I compare the log-based factors, the cumulative log-based factors of the predictive density for 3 months ahead forecast between the Gaussian with stochastic volatility and the M skew-T with stochastic volatility. So the red colors mean that the M skew-T is preferred over the Gaussian. And for the variables that show fat tails and asymmetries like industrial production and the VIX, we will see that the cumulative log-based factors is preferred. However, in the case of Gaussian variables like inflation and unemployment, we will see that the models does not give improvement for inflation and unemployment. However, we will see that here we have an increasing chance in this case. So fat tail and skewness can help to forecast better unemployment after the crisis periods. So for the conclusion, here we have proposed VR models with heavy tail and skewness. We also have an R package, so you can easily to replicate that. Our finding is that stochastic volatility really improve point density forecast. However, if we have stochastic volatility in the models, the skewness parameters also become more important. And fat tail is also help to improve in sample goodness effect and also out sample forecast, even though that we find a very slight evidence of skewness in this case. So thank you.